Welcome to this lecture on nanofluidic devices that defy classical Poiseuille flow. We're going to explore how transport in nanochannels violates the fluid mechanics we all learned in our undergraduate courses. Let's start with what we know. In classical fluid mechanics, we have the Poiseuille equation that describes laminar flow through channels. This works beautifully when the channel dimensions are much larger than molecular scales. The Poiseuille equation tells us that the volumetric flow rate Q equals pi r to the fourth times the pressure difference, divided by 8 mu L. This is the foundation of classical fluid mechanics. But what are the assumptions behind this equation? Let me list them for you. First, the continuum hypothesis. We assume the fluid is a continuous medium with no molecular structure. Second, the no-slip boundary condition. We assume the fluid velocity at the wall is exactly zero. Third, the viscosity is constant and follows Newton's law of viscosity. Fourth, the channel dimensions are much larger than the size of individual molecules. This is crucial. Now here's the question. What happens when we shrink our channels down to nanometer scales? When the channel height becomes comparable to just a few molecular diameters. Here's a nanochannel where the height h is only a few nanometers. Now we have individual molecules whose size is comparable to the channel dimensions. All our assumptions start to break down. The continuum hypothesis completely fails. We can't treat the fluid as continuous anymore because we have discrete molecules. Let me give you some numbers to put this in perspective. What is the size of a water molecule? A water molecule has a diameter of about 0.28 nanometers. So here's a question for you. If we have a nanochannel that's 10 nanometers high, how many layers of water molecules can fit? We divide 10 nanometers by 0.28 nanometers, and we get approximately 35 layers. That's not many. With only 35 molecular layers, can we really treat this as a continuum? The answer is no. We start seeing deviations from classical behavior. Let's talk about the first major breakdown, the no-slip boundary condition. In classical fluid mechanics, we assume the velocity at the wall is exactly zero. This is called the no-slip condition. But at the nanoscale, this assumption breaks down. At the nanoscale, we observe what's called slip flow. The fluid can actually slip along the wall. We define a slip length b. The velocity at the wall equals b times the velocity gradient at the wall. If b equals 0, we recover the no-slip condition. In nanochannels, especially with hydrophobic walls, we see significant slip. The fluid near the wall is not stationary. This dramatically changes the flow profile. For hydrophobic surfaces like carbon nanotubes, we measure slip lengths from 10 to 100 nanometers. This is huge compared to the channel size. So how do we modify the Poiseuille equation to account for slip? For a rectangular channel, the flow rate becomes h cubed w delta p over 12 mu L, times 1 plus 6b over h. Notice the correction factor that depends on the slip length. Here's an interesting question. What happens if the slip length equals the channel height? If b equals h, then the flow rate is 7 times larger than the classical prediction. This is a massive enhancement. This is exactly what we observe in carbon nanotubes. Water flows orders of magnitude faster than classical theory predicts. The second major breakdown is that viscosity is no longer constant in nanochannels. Near the walls, the fluid develops a layered structure. The molecules are ordered by the wall, creating regions of different viscosity. Near the wall, the viscosity can be 2 to 3 times higher than in the bulk. We can model the position-dependent viscosity as mu of y equals mu 0 times 1 plus alpha e to the minus y over lambda. The viscosity decays exponentially away from the wall. The characteristic length scale lambda for this layering is typically 1 to 2 nanometers, about 3 to 5 molecular diameters. Now let's talk about one of the most important effects in nanofluidics, the electric double layer. Most solid surfaces in contact with water are charged. Glass, silica, polymers all develop surface charges. This creates an electric double layer where counter-ions accumulate near the walls. The thickness of this double layer is characterized by the Debye length. The Debye length lambda d equals the square root of epsilon 0 epsilon rkbt divided by 2 nae squared. I. Here I is the ionic strength. Let's calculate this for typical conditions. What's the Debye length in 1 millimolar salt solution? We can use the approximation lambda d equals 0.3 nanometers divided by square root of I in molar. For 1 millimolar, that's 0.3 divided by square root of 0.001, which gives us about 9.5 nanometers. In very pure water with low ionic strength, the Debye length can extend to a full micrometer. The double layer fills the entire nanochannel. Now here's the key point. What happens when the channel height is comparable to twice the Debye length? When the channel height h is less than 2 lambda d, the double layers from both walls overlap. The entire channel is filled with excess counter ions. This creates a space charge that dramatically affects flow. This double layer overlap leads to powerful electrokinetic effects that have no classical analog. One of the most important phenomena is electroosmotic flow. When you apply an electric field along a nanochannel with charged walls, the entire fluid starts moving. The electroosmotic velocity equals minus epsilon 0 epsilon r zeta divided by mu, times E zeta is the zeta potential at the wall, and E is the applied electric field. Notice something amazing. The flow profile is plug-like, not parabolic. The entire fluid moves at nearly the same velocity. This is completely different from pressure-driven Poiseuille flow. Let me do a quick calculation. What's a typical electroosmotic velocity? A typical zeta potential for silica is minus 50 millivolts. Let's apply a field of 1000 volts per meter. Plugging in the numbers. Epsilon r for water is 80, epsilon 0 is 8.85 times 10 to the minus 12, zeta is 0.05 volts, and viscosity is 10 to the minus 3. We get about 3.5 millimeters per second. That's quite fast for a microfluidic system. Now let's talk about one of the most fascinating aspects of nanofluidics, ion selectivity. Here's a question. What happens to negatively charged anions when you try to push them through a negatively charged nanochannel? The anions are repelled. The electrostatic repulsion creates an energy barrier that's many kBt high. The anions are essentially blocked from entering the channel. Only the cations can pass through. The nanochannel acts as a cation selective membrane. This is exactly how biological ion channels work. We can achieve selectivities greater than 100 to 1. The cation current can be more than 100 times larger than the anion current. Another fascinating phenomenon is ion current rectification. This is like having a diode for ions. Imagine a conical nanochannel that's narrow on one side and wide on the other. When you apply a voltage in one direction, you get high current because ions can easily enter the wide side. But when you reverse the voltage, ions have to enter through the narrow side where the energy barrier is very high. The current is much lower. You get rectification. Rectification ratios can range from 10 to 1000. This is a purely nanofluidic effect with no classical analog. Let me show you how surface charge affects the actual flow rate in nanochannels. Here's a non-trivial question. Does having a charged surface increase or decrease the flow rate compared to an uncharged surface? The answer is, it depends. The surface charge creates a complex interplay between electrokinetic effects and viscosity. The total flow is the sum of pressure-driven flow and electrokinetic flow. These can either add or oppose each other. If you're trying to push ions with the same charge as the wall, the electrokinetic flow opposes the pressure-driven flow. The total flow rate is reduced. But if you're pushing ions with opposite charge, the electrokinetic flow helps. The total flow is enhanced beyond the classical prediction. Another important effect is concentration polarization. This happens at the entrance and exit of nanochannels. When ions flow through a selective nanochannel, they accumulate on one side creating an enrichment zone, and become depleted on the other side. This creates huge concentration gradients. The concentration ratio can be as high as 1000 to 1. You can concentrate ions by 3 orders of magnitude. This effect is exploited in lab-on-chip devices for pre-concentration. You can take a dilute sample and concentrate it by a factor of 1000 in seconds. Now let's quantify when classical theory breaks down. We use the Knudsen number. The Knudsen number equals lambda over L, where lambda is the mean free path and L is the characteristic length scale. For liquids, we don't have a well-defined mean free path, so we use the molecular diameter instead. The liquid Knudsen number equals the molecular diameter divided by the channel height. When the Knudsen number exceeds 0.01, deviations from classical theory start to appear. When it exceeds 0.1, classical theory completely fails. You must use molecular dynamics or kinetic theory. Let's calculate the Knudsen number for our 10 nanometer water channel. Knudsen number equals 0.28 divided by 10, which is 0.028. We're right at the boundary where deviations start. So how do we actually study these systems if classical theory fails? We use molecular dynamics simulations. In molecular dynamics, we simulate every single molecule. We solve Newton's equations of motion for thousands or millions of molecules and see what happens. These simulations let us directly observe phenomena like slip flow, molecular layering near walls, and ion selectivity. They validate our theoretical predictions. The problem is computational cost. Molecular dynamics scales as n squared, where n is the number of molecules. Large systems are extremely expensive. Let's talk about applications. One of the most exciting is DNA sequencing through nanopores. You thread a DNA molecule through a nanopore. As each nucleotide passes through, it modulates the ionic current. By measuring the current, you can identify the sequence. This technology only works because of nanofluidic effects. The ion selectivity and current modulation are purely nanoscale phenomena. Nanopores give you single molecule sensitivity. You can detect individual DNA bases as they pass through. Another major application is desalination using nanoporous membranes. Carbon nanotube membranes with sub-nanometer pores can exclude salt ions while allowing water to pass through at extremely high rates due to slip flow. The water permeability can be 1,000 times higher than conventional reverse osmosis membranes. This is because of the slip flow we discussed earlier. The high permeability means you need much less pressure, which dramatically improves energy efficiency. This could revolutionize desalination technology. A third application is energy harvesting from salinity gradients. When seawater meets river water, there's a huge osmotic pressure difference. Ion-selective nanochannels can convert this into electrical power. The maximum power density equals RT over F times delta C times the natural log of C2 over C1. This is called blue energy. The global potential for blue energy is about 2 terawatts of power. That's roughly 10% of current global energy consumption. Now let's discuss the theoretical frameworks we use when continuum theory fails. First, molecular dynamics. This is brute force but exact. You simulate every molecule. Second, density functional theory. This uses statistical mechanics to calculate density profiles and free energies. Third, kinetic theory based on the Boltzmann equation. This is a mesoscale approach between continuum and molecular. Fourth, modified continuum theory, where we add correction terms to classical equations. This is the most practical for engineering design. The workhorse equations for nanofluidic modeling are the Poisson-Nernst-Planck equations. The Poisson equation relates the electric potential phi to the charge density ρ. Del squared phi equals minus ρ over epsilon 0 epsilon r. The Nernst-Planck equation describes ion transport. The time derivative of concentration equals minus the divergence of the flux. The flux has two terms: diffusion proportional to the concentration gradient, and migration proportional to the electric field gradient. These equations couple electrochemistry and hydrodynamics. You have to solve them together with the Navier-Stokes equations. How do we experimentally verify these theoretical predictions? It's challenging because we're working at the nanoscale. First, we measure current voltage characteristics. The shape of the IV curve tells us about ion selectivity and rectification. Second, we measure how conductance varies with salt concentration. At low concentrations, surface charge dominates and conductance becomes concentration independent. Third, We measure streaming currents and potentials when we flow liquid through nanochannels. This directly probes electrokinetic coupling. Fourth, we use single-molecule fluorescence to directly observe molecular transport through individual nanochannels. Let's discuss scaling laws. How do these effects scale with channel size? The slip effect scales as B over H. As channels get smaller, slip becomes more important if the slip length stays constant. Electric double layer overlap scales as lambda D over H. Smaller channels mean more overlap and stronger electrokinetic effects. Ion selectivity is exponential in the energy barrier. Even small changes in channel size can cause orders of magnitude changes in selectivity. Here's an interesting design question. What's the optimal channel size for desalination? The answer is 0.6 to 0.8 nanometers. This is just above the size of hydrated ions. Smaller and you block water, larger and you lose selectivity. Let me conclude by discussing future directions in this field. First, we're developing nanopores in two-dimensional materials like graphene. These have atomic scale precision in thickness. Second, active nanochannels where we can dynamically control surface charge or channel geometry with external stimuli. Third, exploiting coupled transport phenomena where ion flow drives molecular motion or vice versa. Fourth, exploring quantum effects when channels approach sub-nanometer scales. Water confined to a few angstroms shows quantum behavior. Let me give you the bottom line takeaway from this lecture. Classical Poiseuille flow is based on continuum mechanics and the no-slip boundary condition. At the nanoscale, both of these assumptions fail catastrophically. We see slip flow, molecular layering, and electric double layer effects. This leads to entirely new physics, ion selectivity, current rectification, and ultrafast transport that exceeds classical predictions by orders of magnitude. The applications are transformative: DNA sequencing, water desalination, and energy harvesting from salinity gradients. The theory requires a combination of Poisson-Nernst-Planck equations, molecular dynamics simulations, and density functional theory. Let me leave you with the key dimensionless parameters you need to remember. The Knudsen number tells you when continuum theory breaks down. The ratio of Debye length to channel height tells you when double layer overlap becomes important. The ratio of slip length to channel height tells you when slip flow dominates. The dimensionless surface potential tells you when electrostatic effects are strong compared to thermal energy. Thank you for your attention. I hope this lecture has given you a deep appreciation for how nanofluidics defies classical fluid mechanics. The field is rich with fascinating physics and transformative applications. Are there any questions?